Okay, so welcome back to part 2 of continuity and differentiability. Obviously, if you haven't watched part 1, you should probably do that before continuing with this video. In the last part of the lesson, we discussed the concept of continuity, which is what you get when a function can be drawn out without lifting your pen. Now, in this part, we'd like to continue with the second half, which is a discussion on differentiability. So let me start by actually drawing on a smooth function this time. Now we would say that this function over here is smooth, because there's no sudden changes in the slope, like there was in this case. So we can say that a differentiable, or smooth function, is just a function that has no sudden changes in its slope. Now just like we did for continuity, writing down an equation for differentiability is also going to require us to pick a random x-coordinate as well. Now because we want to investigate changes in the slope, let me go ahead and actually investigate the slope between these 2 points over here. Now in order to actually find the slope between these 2 points, let me draw a triangle beneath the secant. Now the width of this triangle is just equal to x minus the length a. Then we can also say that the height of the triangle is just f of x minus f of a. Now this secant over here doesn't actually have the same slope as the curve over here. But if we actually did bring our points a little bit closer, then you'd notice that the secant line is actually very close to the slope of the curve. So I don't know about you, but I actually see a little bit of a limit brewing here. I'll get rid of all the extra markings for a second, just to help you see exactly what's going on. Now we already said that limits have to be the same from both sides, so let me make a copy of this point on the other side. The key condition for a function to be smooth is that if you bring both of these points closer to this point, you'd expect this corner over here to look like it's almost going away. Let me actually demonstrate this. So as you can see, the big sharp corner that we had before has now smoothed out to something that looks very similar to a straight line. So the idea is, if the slope on the left exactly equals the slope on the right, then we can say our function is actually smooth. So that means our condition for differentiability is actually pretty straightforward. All we need is for the limit of this slope to be defined as x gets closer and closer to a, as we saw. Now the slope is just given by the rise, which is f of x minus f of a, and then we divide by the run, which in this case is just x minus a. So the condition here is pretty straightforward. You simply want this limit to be defined, so whether you come in from the left or the right, the slope should be exactly the same. It's also important to note that f of a also has to be defined, otherwise it's impossible for your function to be differentiable. And to actually see this condition in action, let me go ahead and give you one function that is differentiable and one that isn't, so you can see how they fail and pass this test. So first off, I brought back the exact same v of x that we had before. And the second function I have here is just a really simple parabola. Now this time I'll just start by drawing both of their graphs. Now I hope you'll agree that this function over here does not look smooth. But this function over here actually does look pretty smooth. Now in both cases, I'm going to test whether each one is smooth at x equals 1. So first we're going to focus on this function on the left. Let me start by picking a point that's very, very close to 1 on the left. So again, 0.999. Now in this case, the limit on the left is just given by this formula over here. So let me write it out. So here we've chosen x to be 0.999 and a is of course 1. And of course in this case the function we're dealing with is v, so we should also replace that as well. Now we can go ahead and make these substitutions, actually replacing x for 0.999 and 1 respectively. And of course if we actually subbed in v of 1, we'd notice that 1 minus 1 is just 0, so we just get 0. So after substituting, we notice that our left limit is just minus half. Now we should repeat this for the right limit, so this time we'll pick 1.001 and repeat the whole same process. So once we've completed all this, we notice that the limit on the left is minus 1/2, and the limit on the right is exactly 1/2. Since the limit on the left is not the same as the limit on the right, then we can immediately conclude that this function is not differentiable. Now this time we're going to repeat the exact same exercise with this function on the right. Again, I'm going to pick 2 points, one at 0.999 and 1 at 1.001. Now the limit on the left is again going to be f of 1 minus f of 0.999. Now since our function is just x squared, we can just go ahead and square this, and then the bottom is just 0.001. So after we plug everything into the calculator, we notice that the slope on the left is approximately equal to 2. It's 1.999. Now we can repeat this with 1.001 as well. So the limit on the right this time is just f of 1.001 minus f of 1 divided by 1.001 minus 1. Now again, f of 1.001 would just be 1.001 squared, and so on. So as you can see, in this case, the limit on the left is approximately equal to 2, and the limit on the right is also approximately equal to 2. If you were to add more 9s here and more 0s here, you'd notice that both of them are just going to keep getting closer and closer to 2. So therefore, in this case over here, the limit from the left and the right are exactly the same, and therefore this function is differentiable. So I hope this idea is now clear to you. The function on the left is not smooth, so we notice that the slope from the left and from the right were not the same. But this function over here is actually smooth, so the slope from the left seems to approach the slope from the right. And this actually completes our example on differentiability. Now from these definitions, I hope it's clear that a function can be continuous without being differentiable. But now we ask the opposite question. Is it possible for something to be differentiable but not continuous? Let me show you on a new page. To directly answer the question, no, it's not possible. A differentiable function is always continuous. Now this was definitely not obvious to me the first time I saw it. So what I'd like to do is I'd like to give you a non-rigorous proof that it always has to be true. So to give you an idea of why this has to be true, remember we're taking the limit as x approaches a. Therefore I can say that x is approximately going to be equal to a. They're going to be very, very close to each other. Now because x is approximately equal to a, we can move a to the left hand side and say x minus a is approximately equal to 0. Now let's write down the definition for differentiability. Now sure, we can take the limit as x approaches a, but we can say that this thing over here must approximately be equal to this s over here, just like we did in our example. Now we can take this condition and multiply both sides by x minus a. Now as we said before, if x is approximately equal to a, then x minus a has to be 0. And this means that this right hand side over here also has to approximately equal 0. And now finally, let's take this to the right hand side as well. Now since we rearrange this to get this, that means that anytime this is true, this must be true as well. In other words, we're saying that this implies that this has to be true. Now if you look carefully at this, we're actually saying that f of x is approximately equal to f of a. Or in other words, when x is approximately equal to a, then f of x has to be the same thing as f of a. Now if you look carefully at this, this is just the same thing as the definition of continuity. It's just telling us that when x is approximately equal to a, then f of x is the same thing as f of a. Or if we look at this on the graph, when x and a are very close to each other, then their y coordinates are also going to be very close to each other. And this is just the same thing as continuity. Now because this is the definition of differentiability, and this is the definition of continuity, then we're saying that differentiability implies continuity. Or in simpler words, any function that is differentiable must be continuous as well. And this actually makes the definition of differentiability a little bit clearer as well, because it means that functions like this one are not going to be differentiable, despite the fact that the gradient on the left seems to be the same as the gradient on the right. Therefore, for a function to be differentiable, not only does it have to have the same slope on both sides, but it also has to be connected. And as we know, connected functions are just called continuous functions. And this actually really clarifies what we mean by a smooth function. So to summarize this lesson, we talked about two types of conditions that you can have on functions. We said that continuous functions are just functions that you can draw without lifting your pen, and differentiable functions are just smooth functions that don't have sudden changes in the slope. We said that continuous functions don't have to be differentiable, but every single differentiable function must be continuous. And with this, we've actually completed our discussion on continuity and differentiability.